Hey everyone, today I'm competing in Educational Codeforces round 111, which is starting in just a couple of seconds. Here we go. Alright, cool. AC on A. It's actually a really fast solve. I'm not sure I've ever gotten a problem that quickly. Duh. Okay, why don't I have the submission portal? Why am I not logged in? Strange. Okay. Well, that's fine, I guess. Why is it taking so long? Okay, accepted. Nice. Alright, so problem C. Let's just refresh all of these to get the submission open. Alright. are we getting to 0 so quickly? Oh, let's see. Such a big difficulty get from B to C, I feel like. I know, I always find these sorts of problems annoying. Okay, now we're getting 13, so that's still not good. Wait, I've been misreading this whole time. I, J, and K do not need to be sorted. Shoot, okay. Oh wait, no, they do. What am I talking about? Yeah, but it does mean that with this sequence cannot be decreasing either. Okay, so Okay, well, at least I don't think I was I don't think, or yeah, I don't think I'm, my error is something that like, or I don't think that the new version of the problem is any easier. Okay, I'm going to comment out these debug statements just to be safe. I hope I'm not way behind by this point. It worries me that C took me so much longer than these first few problems did, because I feel like I'm wondering if I overcomplicated it, but I don't know. Huh, okay, this is interesting. I feel like I'm gonna need combo for this. absolute. Can't just use bars to represent absolute value. Okay, so Okay, finally. Yeesh. This went from 0 to 100 very quickly. Ah, crap, okay. Let's see. All right, there we go. Okay, I see how to do this. Should have done this first, actually. I feel like this is much easier. Is this gonna be fast enough, actually? Let's see. So, yeah, I think this should be okay. they're certainly giving us plenty of sample cases. Appreciate that. Yeah, I actually think this is easier than, I mean, honestly, I know for me this is easier than either C or D, so it's unfortunate that I took the problems in order here. 5-second time limit with queries, this seems like it might be unpleasant. Alright, let's see. pop. Shoot, what did I just do? Oh, I'm dumb. If this solution is correct, this contest has the most... just has a stupid difficulty curve, honestly. Like, literally, I feel like if this is right, then C through F are all pretty much the same difficulty. Okay, but this is wrong, so... Trying to decide whether my idea is wrong or there's just a bug in my implementation. Oh, actually, I think my idea is wrong. Okay, that makes sense. Okay, I think I see how I can modify this. Well, do I see? I think I sort of see, maybe. How do I print no here? Let's see. All right, awesome. So that's the contest. A little bit slower than I would have liked, but overall pretty solid performance. See, no idea whose alt this is, but can't be too disappointed at placing behind Jangly and Neil. That's kind of to be expected for now anyway. Looks like there are a number of people who have the potential of passing me, largely because my C and D were pretty slow, but luckily I caught up by making pretty good time on E and F. So yeah, I'll be interested to see if anyone has nicer or shorter solutions to C or to D, because I definitely feel like I spent more time than I needed to on those, to the point that I felt like I found all of these problems to be approximately the same difficulty, and that's backed up by if anything, I think E was maybe the easiest for me of these four, which is definitely not what the solve statistics suggest. It sort of seems like, I guess one could make the argument that E is as easy as or easier than D, and it only has fewer solves because people look at D first. But I also kind of wonder if I made C harder than I had to be, because C took me 16 minutes, D took me 25, E took me 8 minutes, and F took me, I guess that's 27 minutes. So I guess, this kind of suggests that I found E easier than C, C easier than D, and then D just barely easier than F. Yeah, kind of curious about this one. There's a way to do it more easily, but I guess we'll find out later. Okay. And let's see how many people have the chance to pass me. So probably quite a few, actually. Yeah, I think anyone currently, all 11 of these people theoretically could do it, and a lot of them have quite a bit of time to do so, since my time is 2:12 and the penalty is about 80 minutes right now. So actually not these last few, but any of these guys could do it. So we will see what happens, I guess. And of course, there's always a chance I get hacked, but hopefully that doesn't happen. All right, let's talk through solutions. Okay, problem A, find the array. Let's call an array A consisting of n positive integers beautiful if the following condition is held for every I from 1 to n. Either A sub I is equal to 1, or one of the numbers A sub I minus 1 or A sub I minus 2 is also an element of the array. We're given a positive integer s, and we want to find the minimum possible size of a beautiful array with the sum of elements equal to s. Okay, so I think when you see a problem like this, we're trying to achieve a certain sum while minimizing the number of elements in the array. And so a logical first question to ask is, what's the maximum sum of the elements in an array given the size? And so for example, let's work through a few small cases. So first of all, let's say that n equals 1, then the only array we can have is 1, because for any greater number, these conditions won't be satisfied. And so the sum is going to be 1. For n equals 2, again, our first element has to be 1. And then afterwards, this lets us add either 2 in this case or 3 in this case. So for maximizing the sum, we'll add 3. And so that gives us a sum of 4. When n equals 3, works the same way. We add 1 and then we add 3, and then now the greatest number we can add is 5. So our sum is going to be 9. And you might be seeing a pattern here. You might be what you should be observing by this point is that the best we can do with an array of size n is to take the n smallest positive odd integers, which have sum n squared. And in fact, it's we can prove by induction that the sum of the first n positive odd integers is n squared. But what that implies is that with n elements, the maximum sum is n squared, achieved by a pattern 1, 3, 5, all the way up to 2n minus 1. Okay, and so what this implies is that since s has to be, since s is the sum of our n elements, since the maximum sum is n squared, this implies that s is less than or equal to n squared, or alternatively, n is greater than or equal to the square root of s. So that gets us a lower bound on n, and so we know that n has to be at least square root of s. Now the question that we have to answer afterwards is this lower bound tight? Or in other words, if n is greater than or equal to the square root of s, is achieving such an s always possible? And the answer is yes. And I didn't prove this rigorously in the contest just because it made intuitive sense, and I mean also it's a div 2a, so I think once you get to a certain point in solving a div 2a, you can sort of assume that the math is going to work out nicely. And so the proof is not too hard to conceptualize, but it is a little annoying to write out. But basically the idea is that, let's say we're looking at the n equals 3 array, and we start with 1, 3, 5. But let's say that we actually want to make the sum, 6. We have a pretty easy way to just kind of gradually decrease elements in the array. So for example, what we can do is we can decrease 5, and now for 4 we're still going to have 4 minus 1, which is 3 in the array. And so now we can't decrease, we can decrease 4 again. Yeah, we can decrease 4 again. So yeah, so now it can be 3, and 3 is fine because 1 is in the array. And now we can decrease it again to 2, and then 1 plus 3 plus 2, and the sum is going to be 6. And in general, if n is equal to 3, then s is greater than 4, because if s were at most 4, we would take n to be 2. And s is less than or equal to 9. So what we can do is we can take 1, 3, and then something from 1 to 5, and we can verify that anything from 1 to 5 is going to be valid here, because if it's because 1 is automatically valid. If it's 2 or 3, then the fact that 1 is in the array makes it valid, and if it's 4 or 5, the fact that 3 is in the array makes it valid. And so we can then and so we can add something from 1 to 5, and that gets us all the numbers from 5 to 9. And the same logic works no matter what n is. And so because of that, we just need n to be greater than or equal to the square root of s. And to implement this, I don't want to use the built-in C++ square root function, because it can lead to some floating point precision issues when S is, or especially when S is large. That probably won't be a problem here just because S is bounded by 5,000. But just in case, I implemented this manually. And so I just found the first I such that I squared is greater than or equal to n. I guess I used n in my code instead of s. And then I printed out that I. All right, problem B, maximum cost deletion. You perform the following operation until this binary string becomes empty. We have to choose a consecutive substring of equal characters, erase it from the string, and combine the remaining 2 parts. And when we delete a substring of length L, we get A times L plus B points. And we want to calculate the maximum number of points we'll score in total if you're going to make the given string empty. Okay. So the first thing to do here is let's separate out the A and the B components of our scoring function. And our A component is actually really easy to deal with, because realize that the total length of all of our substrings is going to be n. And so that means that the sum of A times L over all substrings is A times n. And that's basically because you can think of this as getting A points for each character you delete. We're going to be deleting n characters in total. So this is going to be A times n. So now what we need to deal with is the second term, which is essentially B for each substring you delete. So there's 2 cases. And so here what we're going to do is we're going to think about this in terms of 2 cases. If B is positive, or in this case I'm saying B is non-negative, obviously, and B is 0, it doesn't really matter what we do with it. Our score goes up when we delete more substrings, so we should delete as many as possible. And B is less than 0, our score goes down when we delete more substrings, so we should delete as few as possible. Alright, now the positive B case is pretty easy, because if we want to delete as many substrings as possible, what we should do is we should just delete every string on its own as an individual substring. So we just delete all n characters individually, and then we get the answer is A times n plus B times n. The B is less than 0 case is a little more intricate. The idea here is so first of all, since we're trying to delete as few substrings as possible, obviously, we should only delete entire blocks of substrings. So, for example, if we're looking at the second sample case, 1, 1, 0, 0, 1, we would not delete just one of these zeros. If we would just delete both of these zeros at once. And so the idea here is we can show, essentially we're going to alternate between blocks of zeros and blocks of ones. So, let's see, if we condense everything to every block to 1 character, then it might look like 1, 0, 1, 0, 1. Or this sample case would be 1, 0, 1. And it can be shown that the best way to do this is to delete both of these zeros and then delete all the ones together. Or in general, we should just delete every block of whichever type appears the fewest times, and then we can delete every character of the other type in one go. And that's how many times we're going to need to add B in this case. And so I can show you how I implement that. So here, this is the positive B case, relatively straightforward. For the negative B case, the way I do this is I let K be the number of blocks of the same character. And I compute K using this loop because I know a new block starts whenever the current character is different from the previous one. And then I show that the number of blocks of the less common type is going to be the floor of K divided by 2, which in C++ is just K divided by 2. And so I add K times B, and then I add 1 times B for that one operation we use to delete all the remaining character, or all the whichever character appears in more blocks. All right, so that's B. So problem C, Manhattan subarrays. So we define the Manhattan distance, and then we say that the 3 points P, Q, and R form a bad triple if the distance between P and R is equal to the sum of the distances between P and Q and the distance between Q and R. And we want to find, or we say that an array is good if it's impossible to choose 3 distinct indices such that the points B sub I, B sub j, j, and B sub k, k form a bad triple. And we're given an array A, and we want to count the number of good subarrays of A. Okay. So first, let's talk about when 3 points form a bad triple. And I'm actually going to pull up a Zoom whiteboard to do this because I think that's going to make this easier. There's a lot of visual intuition going on here, and so I think it'll make more sense that way. And let me make sure this is still recording. Yep. Okay, perfect. All right. Okay. So let's say that we've got this grid, and I'm drawing using my mouse, so this will not be particularly pretty. Okay. And let's say we've got, let's see, so let me make sure, so let's say we've got P down here and R up here. Now recall that the Manhattan distance is basically the distance if we can only go straight in vertical or horizontal, in the vertical or the horizontal direction. And if Q is anywhere in this grid, and the idea, and then another key bit of intuition here is that this equation essentially represents that there's a path straight from P to R that goes through Q, or that like there's a shortest path from P to R that includes Q. And realize that the shortest paths from P to R are just any like horizontal / vertical path in this grid that that does not like leave the boundaries between P and R. So for example, this is the shortest path. 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 All of those are shortest paths from P to R. But on the other hand, this, if we go like out and then around and then back in, is not a valid path. So this distance is not going to be equal to the d from P to R. Okay. And so as long as Q is within the box defined by P and R, let's say Q is here, then it's going, or then this inequality, or this equation is going to be satisfied, because and we can see that visually if we draw the path like so. We can see, okay, this bit represents the distance from P to Q. This bit represents the distance from Q to R. And this whole thing is the distance from P to R. But in contrast, let's say that we put Q down here. And then it doesn't work. We would have to do something like this, and this would be a shortest path from P to Q and a shortest path from Q to R, but not a shortest path from P to R. And so we can see that the equation doesn't hold. Okay. All of this is to say that P, Q, and R form a bad triple if and only if Q is within the box bounded by P and R. And more formally, the way we can say this is that xq is between xp and xr, and yq is between yp and yr. And if we apply that to this problem, if we're looking for 3 distinct indices such that b sub I, b sub j, and b sub k with their indices form a bad triple, then then what that means is whichever index is in the middle, it needs to have the value in the middle. And what that means is if we assume without loss of generality that I is less than j is less than k, then either b sub I is less than b sub j is less than b sub k, or b sub I is greater than b sub j is greater than b sub k. And what this is equivalent to saying is the first line is equivalent to saying there's an increasing subsequence of length 3 and or there's a decreasing subsequence of length 3. And unfortunately, I just realized what the easier solution to this problem is than the one I implemented. So let's see. I'm trying to think to make sure that what the idea that I'm thinking of works, but if this does, then I want to explain that one to you guys rather than the one I actually wrote up, because I think that the one that I wrote up is, or because I think that the one I actually coded is much messier. Okay, yeah, I'm going to explain this new solution, and because I think that's much easier to code, and I kind of assume that that's what all the people who solved C in less than 10 minutes did. Okay. So what we're going to do is we're going to figure out which subsequences have none of these first kind of triples. No increasing subsequences of length 3. And then we can use an analogous process to figure out which subarrays have no decreasing subsequences of length 3, and we can sort of combine the results. And the way we can do this is we'll iterate over the middle element. And the idea is that we're going to try to find the last smaller element for each possible j. So the closest b sub I, such that I is less than j and b sub I is less than b sub j. And likewise, we'll find the next larger element. So for each, and basically what we're doing is for each j, find the closest possible I and k. And the way we can do this is by maintaining a set. And so let's say, for example, that we're trying to find the closest possible I. Then what we'll do is we'll maintain a set of the of elements sorted by we'll maintain a set of elements sorted by their value, and whenever we add a new one to the set, we'll erase all of the smaller ones that already exist. And the idea is that at this point, the set is essentially going to store only the minima, or only the elements that are smaller than every element afterwards that we've seen so far. That is only the elements that could be our choice of I. And then we'll find the next, and then in order to do this, we'll find the next, and then in order to find the correct value of I, we'll find the closest, or we'll then find the next element in the set smaller than b sub j. This is a pretty well-known technique. There's some good articles about it. I'll try to find one and put it in the description if I remember, because I think that's going to explain it better than I could here. But that's basically how we find the closest possible I. And so we can do the same thing to find the closest possible k. And then the idea here is that if a sequence starts at I or earlier, it must end at k, or it must end before k. And so we end up with n constraints of that form. And after that, we can then use those to figure out what's the for each x, what's the greatest y such that a sub x plus 1, all the way up to a sub y is a valid subarray. And we can use that result to figure out our answer. So let me show you, I'll show you my code. I'm not going to go through this go function real quick because it essentially, oops, I went to a new page too soon. the go function is, I actually don't know if it's that much, if this other solution is that much nicer. I'll be interested to see what other people did. But this go function essentially computes this vector, or it computes the number of valid subarrays starting at x, or starting at each position x. And the first time I run it, it checks that there are no increasing subsequences of length 3, and the second time I run it, I multiply everything by -1 in order to check for decreasing subsequences of length 3. Because if you multiply by -1, then all of the increasing subsequences become decreasing subsequences. Okay, so so I compute those, and then the idea here is that whichever sequences or subarrays are valid are going to be the first. Like if they're case valid subarrays starting at position x, then those are going to be the first case subarrays. And so if they're like, let's say that there are x subarrays starting at I that satisfy the first condition, y subarrays and y subarrays starting at I that satisfy the second condition, then they're going to be min of x, y subarrays satisfying both conditions. And so that's why I add the minimum of my 2 answers to my final result. All right, yeah, this was a bit of a tricky one to explain, I think, and I think the next problem D is going to be C, D, and F, I think, on this contest are all difficult to explain, so I would definitely encourage you to read the editorial if you're confused, and then feel free to ask questions in the comments section if the editorial doesn't answer them. All right, but let's look at problem D. Let's call an integer array good if a sub I is not equal to I for each I. And let's let f of a be the number of pairs such that a sub I plus a sub j is equal to I plus j. An array is excellent if it's good, if all of its elements are between L and R, and if it achieves the maximum possible value of f of a. And we want to find the number of excellent arrays, modulo 10 to the 9 plus 7. All right. Now, a common trick when we're given expressions of this form is to try to make the I term and the j terms independent of each other. And so let's put all the terms involving I on one side and all the terms involving j on one side. So we have a sub I minus I is equal to j minus a sub j. And so let's let b sub I equal a sub I minus I for all I. Then this is equivalent to saying b sub I is equal to negative b sub j. All right. Now what we can show is that the best value of f of a occurs when b sub I equals x for some x, or n over 2 values of I, and b sub I is equal to negative x for n over 2 values of I. I'm not going to go through the proof here. There's you can sort of see this intuitively in that the number in that I think so all the elements should have the same absolute value, because any two elements of B with different absolute values can't satisfy this equation. And then so then if we say that all of them are going to have the same absolute value, then let's say k copies of x n minus k copies of negative x, then the total value of f is equal to k times n minus k, since a pair is valid if it has a copy of x and a copy of negative x, and that's nk minus k squared, and this is maximized when k is n over 2. And then when n is odd, one of these values should be floor n over 2, and the other should be ceiling of n over 2. Okay. So now we need to figure out how we can count arrays satisfying this condition. And what's particularly tricky here is that there could be a whole lot of possible values of x, because because L and R can range from can be up to 10 to the 9. And so, as a thought experiment, let's say that we've chosen some x, or so, well, I guess actually let's say this. So another good question to answer is, when can we have b sub I equals x? Well, we know L is greater than a sub I is less than or equal to a sub I, which is less than or equal to R. So L minus I is less than or equal to a sub I, which is less than or equal to a sub I minus I, which is also b sub I, which is less than or equal to R. So we need L minus I, or sorry, R minus I, sorry, to be less than or equal to x, less than or equal to R minus I. And so in general, and so what this tells us is that b sub I can equal x when x is between L minus I and R minus I. But we can see that L minus, and so let's say that x is positive for now, then L minus I is never going to be positive. So if x is positive, then the main constraint here is x less than or equal to R minus I. And in particular, rearranging this gives that I is less than or equal to R minus x, which means that there are R minus x valid positions where b sub I can equal x. And if we want to have b sub I equals negative x, then we get similar constraints, except now the key issue is L minus I has to be less than or equal to negative x. And that implies I has to be greater than or equal to x minus L. And what that means is that there are going to be n minus x minus L plus 1 positions in this case, or where b sub I can be negative x. Okay. So the first thing let's think about here is, so I guess an important question that you should be thinking about at this point is, how are we going to get through this without looking at each possible value of x individually? And the answer is, it looks like it is what you can tell from these equations is that whenever x is not particularly close to L or to R, then both of these values are going to be greater than or equal to n, which means that any element can be x or any element can be R. Or more formally, so we're going to ask, when can every element of A be, when can every element of B be either x or negative x? So we need R minus x to be at least n, which implies x is less than or equal to n minus x is less than or equal to R minus n. And then we need n minus x minus L plus 1 to be greater than or equal to n. And some rearranging gives that, let me see, did I do my math right here? Let me take a look at my code real quick just to make sure that what I'm doing is consistent with that. Oh, whoops. Sorry, this should be, I made a mistake with my inequalities here. Let me scratch this out real quick. This should read x is less than or equal to, this should read I is greater than or equal to x plus L. So there are n minus x plus L minus 1 positions. And so that means that this should be a plus. And then when you rearrange the inequality, you end up with x is greater than or equal to 1 minus L. or sorry, x is less than or equal to 1 minus L. So that means that this is going to be satisfied when x is equal to min of r minus n and 1 minus L. And in this case, what happens is any element can be x or it can be negative x. And so the only decision we have to make is to choose which one is x and which ones are negative x. So there are x such cases, and n choose n over 2 options per case. So this adds x times n choose n over 2 to our answer. The one edge case is if n is odd, then their x choose floor of n over 2 ways with floor of n over 2 values equal to x, and x choose CL n over 2 when their CL n over 2 values equal to x and floor n over 2 equal to negative x. But that'll make some more sense when I go over it in my code. All right. So now we just have the remaining values of x to deal with. And what we can show, in particular, is if and I'm not going to go through the math. It's pretty similar to what I just did, except with slightly different values. What I can show is that when x is greater than the minimum of r and n plus 1 minus L, then either no element of B can be x or no element can be negative x. So that's definitely bad. And so what that means is that there are only n values of x that we still need to check. So now we're at the point where we can check those values manually. So let's go through how we can do that. So there are r minus x. So we're checking an individual value of x. There are r minus x positions that can be x, and n minus x plus L minus 1 positions that can be negative x. And so then the idea here is the positions that can't be negative x have to be x. And there are x plus L plus 1 of these. Oh, sorry, this should be sorry, I've got my signs flipped again. I think this should be plus, yeah, and then I got it right up here. And so then this should be plus, and then okay, and so there are x plus L minus 1 positions that can't be negative x. So these have to be x. Likewise, n minus r minus x positions can't be x. So these have to be negative x. And so the number of ways here is there are n minus the sum of these two things. So n minus x minus L minus 1 things that can take either position, and then we need n over 2 minus x plus L minus 1 to be x, or to be positive x. And so in this case we add this thing to our answer. And so that's pretty much the problem. It's basically just a lot of annoying algebra. I implement the solution here. So cap stores this minimum that I identify here. So, and then I add and then I use this get function to compute this thing here. And so I add that to our answer, and then I do the same for all the next values. I go up to cap plus m plus 10. This isn't necessary, but my get function will print 0 if for like the values that are too high. So this just means that so using plus 10 here just meant that I don't need to figure out precisely where the edge case is. Yeah, and so here again, if n is odd, then the reason like I need to handle the n odd case differently is that if n is even, then n over 2 values of x and n over 2 values of negative x is indistinguishable from n over 2 values of negative x and n over 2 values of x. But if n is odd, then floor of n over 2 values of x is distinguishable from ceil of n over 2 values of x, and so I need to handle both cases. And then I print out my answer. Again, you can take a look at the editorial for alternative treatment of this math. Okay, problem E. This one is going to be a little easier to explain, thankfully. So we're given a string S. Each character is either a question mark or it's one of the first k lowercase Latin letters. And we're asked to replace every question mark with one of the first k lowercase Latin letters in order to maximize the minimum of the maximum length substrings of each character. All right. So let's see, what's the easiest way to do this? I guess the idea, whenever you're trying to maximize a value like this, especially a value where if you can achieve a certain value, let's say x, then you can always achieve any smaller value y, which is going to hold here because if a substring of length x of all k letters appears, then a substring of length y definitely will. So basically, whenever you have a setup like this, you should always think about binary searching the answer, because that reduces our problem substantially. It means that by binary searching the answer allows us to reduce the problem from what is the maximum value of our string to does there exist a string with a given value? Or is it possible to have at least this value? And so now we want to answer the problem. And so now we focus on the second problem. Okay. And the way we're going to do this is using bitmask DP. And this is motivated by the fact that k is up to 17. This is a small enough bound that it seems like it's designed for us to have a DP with 2 to the power of k states. Because think about it like this. If they didn't intend for us to do bitmask DP, then there's no reason they wouldn't set k to be up to 26. But if k were up to 26, 2 to the 26 times log n would be really high. And so that would be impossible. And so the only feasible reason, or I'm not going to say the only feasible reason, the most likely reason that they include this bound on k for us is to allow us to do a solution that's exponential in k. All right, so that's why we might think to do bitmask DP, and our DP is going to be like this. So DP of m is the least position p such that it's possible, or it's possible to replace all question marks up to position p such that all of the characters corresponding to bits in m have substrings of length v, where we're trying to construct a string with value at least v. All right, so that's our DP formulation. Now, how do we do our transitions? The idea here is we're going to store an auxiliary array next to p of c, where that stores the next starting position of, or the next starting position at or after p, where we can construct a substring of v copies of character c. And let me walk through this with my code. So So first of all, this code just sets up my, so this code down here is for my binary search. So what I do is I first store the CNT array, and CNT stores the number of, or the longest possible streak of a given character that we can construct at each starting point. And then I construct next in here. And what I do is I say, okay, if we can construct a sequence of length v starting at this position with this character, then the next position is right here. And otherwise it's the next position from the next, and then otherwise we look at the next position on the line. And so then I construct DP, or this is my DP table. And what I do is, so first of all, if DP of I is at least n, I continue, and that's because if we're already at character n or beyond, then we've passed all the characters of s, so there's nothing more we can do. But then I iterate over all j, and I iterate only, and I skip j if j is already a set bit in I, if that's something we've already found. And then I find the position of the next streak of character j, and then I add v to get the ending position. And then I set dp of I plus 2 to the j, so I just set j basically to the minimum of whatever it is currently and this new position. And then ultimately, if we can reach this last position in which every bit is set by the time we hit character n, then the answer is yes, and otherwise the answer is no. All right, problem F. Okay, so we've got an infinite pond with n rocks located at integer coordinates. A frog is on a certain rock. It has a jumping distance d, and if the distance is set to some integer k, then the frog can jump to some rock from some rock to any rock at a distance from d minus k to d plus k inclusive. We have to determine, given two integers I and k, if the frog can reach rock I from rock s, given the jumping distance range set to k. All right. Now, what we're going to try, now it seems like processing each of these queries individually is going to be pretty difficult, because I can't really think of an easy way to do so, or to do like an individual query other than just BFS, which is going to take O of n time, and of course O of nq is way too slow. So what we'd like to do is some pre-processing, and the natural thing to try is for each I, what is the minimum k such that we can reach position I with jumping distance range k. And the idea here is that increasing the jumping distance range is never going to make it harder to reach a rock. And so if we compute the minimum valid k, then any greater k is also going to be valid, and we can use that when we answer the queries. And the way we do this is through an algorithm that's pretty bashy. It's vaguely inspired by Dijkstra, but it's kind of got its own twist on it. So here's the idea. What I do is I maintain a queue, and the queue includes pairs corresponding to the distance to a rock, and then the index of that rock. And I process these pairs in here. And the key invariant, which is the same invariant that holds in Dijkstra's algorithm, is that whenever we're processing a given rock, all future rocks will have higher distance than the current rock that we're processing. And this makes sense, right? Like, jumping is never going to decrease our distance or anything like that. And I'm defining distance to be the maximum jumping distance range that's necessary to reach, that's necessary to reach a given rock. Okay. So here's the idea. Any rock that we haven't yet processed is going to have distance at least little d, where d is the distance to our current rock. And so what I do is I call this push function, and what this push function does is it says for all is that it says if we can reach a rock from rock P with distance at most, or with jumping distance at most little d, then set the distance to that rock to D. And as soon as that happens, then we know that every rock that we haven't processed yet has distance at least D. So if we can show that it can be achieved with distance D, then we know that it has exactly distance D. And so we can remove it from our set rem of remaining rocks. And that means, and that's really convenient because that means that we process a rock in this push function no more than once. The next thing I do is I use this add function, and this add function essentially corresponds to saying that this could be the longest that we can add a jump here, but it's going to be longer than any jump we've seen so far. And the reason this works is that if we've already called push, then cases where then push handles the cases where the longest jump has already been seen, and so we use add to handle cases where there's a new longest jump. And so the idea behind add, or the way we make it efficient, is that we only check the positions to the left and the right of P, and we say, okay, if this is the closest we can get to the position to the left or the right of P, then we add those positions to the queue. And the reason this works and the reason that we don't need to look at positions further away, at least for now, is that whenever we here, let me write this down because it's important. So if jumping from rock X to rock Y is not the most efficient way to get to rock Y, where let's say Y is to the left of our jumping destination, then jumping from X certainly won't be the most efficient way to get to any rock to the left of Y. And so the idea is basically that if we jump and then we go further and then we go to the left, but then that isn't the most efficient way to reach a certain rock, then it definitely won't be more efficient definitely won't be the most efficient way to reach any rock further to the left. And so that's the property that this add function uses, and it means that we only need to add two cases, or we only need to look at two possible destinations for each jump. And so initially we add the two possible jumps we can make from rock S, and then for each rock we this call to add essentially says, okay, we found the most efficient way to go to our current rock. Now let's see if we can go further left or further right. And then we call push to handle the cases that really close to the two jump destinations where we've already found, or where a jump we've already taken is the longest, or is going to require the largest range. And then we call add to handle the ones further away. This is obviously a hand-wavy explanation. I think it'll make sense in the editorial, just because it's pretty difficult to outline all of this precisely in audio rather than by text. And so take a look at the editorial. This is confusing, and if you still have questions, feel free to leave them in the comments. Alright, so I think that is about all I have for today. Let me take a look at the standings, see how we ended up doing. Alright, 6th place. It's not bad. Unfortunately, I was behind by only 1 minute, which is sad, but overall a pretty solid performance. There were only 16 AKs, so it's good that we were able to solve the entire set in 1 hour and 20 minutes. But yeah, I think that is about all, so thank you very much for watching.